and let's share it. Okay, so we're back in business. All right. So oops, not the right one. While you guys are having a break, I went to solve this problem. But let me honestly tell you one thing. You may run into a problem with the sign, especially with this equation. You need to try to find a way to make sure that you write the proper equation, okay? Because it's pretty obvious that the base shear here, we call it the base shear, is a shear at the base of the frame, should be equal to this, the external force here. But generally, I prefer to write something like this, I don't know why today I'm doing it this way. I write sigma fx is equal to 0 and I can just throw everything on the same side, But the thing is that I am using a calculator that doesn't originally belong to me. Just somebody forgot at the department for a few years. And I don't know how to work it out, but I can use it. But when I solve the simultaneous equations, it doesn't say the parameter is on the left or on the right side of the equation. Okay. Anyway, you need to be careful with that. I wish I could tell you how, because if I knew how it operated, I would be able to tell you the proper way to write the equation. Generally, the red one here is fine, but when you have the answer, you should try to make sense out of it. Okay. In this case, I know right away that because I have a problem that looks like this, Remember, we pushed the frame from the right. So, and again, this is experience, part of it. So when we have a frame like this, you know that when you push it, it will just have to go to the side like this. And we go to the side like this, this one, because it comes off a little bit, so it should be rotation that looks like this. So I already know that I should have the counterclockwise rotation, right? And you should see as well that you remember your side should be counterclockwise as well. So I can say that I should expect something negative here. All right. And there I go. When I solve, I get the EK zeta be equal to minus 7.14286. And again, you guys, if you have a problem with round off of the number, you can use like maybe 4 or 5 decimals. But I'm showing you here because this is the number that if you use, you probably get the proper moment out. But this is the number that we should not write down on the paper, because it looks kind of crazy. And EK zeta C is again, it's the same. 14286, stuff like that. And EK delta, this is minus 59.5238. And because again, if I look at the frame, this is how it goes, right? So I know that if I look at my column, it should go like this. So I also know that I expect the end moments to be clockwise. So when you use this rotation, plug in to get your calculation, MAB is equal to 2 minus 7.143 minus 1.2 minus 59.52. I get my MAB equal to 57.14. What's the unit? kilonewton. Okay. Kilonewton meter. And my MBA is going to be equal to 4 minus 7.143 minus the same 59.52. That's 5. Okay. This is 42.86. So, you know, so far so good. And then your judgment day will come in with MBC. But generally, you should always get the same number because you get the answer from setting up MBA plus MBC equal to 0. Okay. So if you don't get it equal and opposite in the end, it means that mathematically something bad goes on. So that is because theta B and C are the same, so it's just a 6 EK theta, right? So here I am, minus 42.86 kilonewton meter. So that is pretty much it. And we have, now you have MAB 57.14, 42.86, and here is minus 42.86. Okay, and here should be the same, 57.14, 42.86. There we have it. Okay, so you can use this to solve your shear and your axial and everything. Okay, is there any question? Notice how your bending moment diagram should look like, ladies and gentlemen. Compression on this side, so your bending moment diagram for this column should look like this. Okay, and for the beam, that. And for this column, that. Okay, keep in mind that we always have the point where moment becomes 0 here, here, and here. And we will take advantage of the fact that we have something like this in our approximation method later on. Okay? Is there any question? No. You know, okay, it's fine. So that's the end of one example. Now, generally, I don't begin with the example. I begin with, you know, showing you some frames with this kind of movement. But I didn't mean to try the new approach today, but I just forgot that I should have perhaps begun there. But anyway, this example is simple enough, so it's not a bad place to start. So let's try to see something else. Okay, let's see if we have a situation where, let's say, you know, there used to be a lot of tough exams like this in the past, but you know, maybe it's not that necessary anymore. Okay, so let's see. Generally, every year I would begin by, you know, showing the frame. It looks a bit unusual. Let's say if we have something like this. And let's say I can push the beam with the lateral load anywhere. Now your knowledge will tell you that, definitely you have unknowns. And again, let's say call this A, B, C, D. What unknowns we have is again going to be zeta B, zeta C, and then delta. But now you can see that we use the concept of, axial deformation is negligible. So when you look at this, you should use a different color. Your frame will go like this, right? But when you say your axial deformation is negligible, it means that this delta here must be equal to that delta. Okay? So if you don't approach the problem with the delta, you see that because delta is the same now, but these two members, they are not equal. They are of different lengths. So that means the psi term will be different. Here you have psi AB, and here you have psi CD. Now, psi AB is not equal to psi CD, but the delta is the same. And because psi AB is not equal to psi CD, if you don't convert your psi term into the delta, you will have two unknowns. But because we use slope deflection and we say the axial deformation is negligible, so we can reduce the unknown down to 3. And by converting the psi into delta, now you actually have 3 to handle. If you don't, you will run into problem. So in this case, you can say that psi AB is equal to delta over the length of member AB. And the psi of member CD is of course delta again, but over the length of member CD. So, in terms of equilibrium, it's the same, but, you just have more work, because if you don't convert your psi into delta, you have more unknowns than you can handle. So in the first example that we just finished, I just convert the psi into delta right away. So you don't probably see why I need to do that, but now you can see. Okay, and something special with this is that when you write the sigma fx equal to 0, the sigma moment is the same, right? There's nothing unusual about that. You just need to, let me try to write it with the same length. Okay, so that's okay. Now, when you write the equilibrium equation for member AB, for example, you just need to use the correct free body diagram. So again, if you are okay with equilibrium from your day one, this is nothing new. But again, you say this time, because P is here, so you can look at your member AB and write your moment equation, say, based on your superposition, which means that the first one, I can write my horizontal force based on P alone. Okay, so this is, let's say I need another variable. Let's call this distance A. Okay, so that means this force is P multiplied by A and then divided by length AB, right? Again, this is nothing new, it's just basic equilibrium. But I know some of you hate variable, so you don't really adjust to this very well. And so this becomes the remaining of this, which can be written as P minus P A over length AB, right? Crikey me. That's length AB. Okay, or you can just say, can I say this is AB minus L or something like that? Yeah, sure, why not? Or it's just equal to P AB minus A, divided by the length AB. It's the same, right? And that this is the force due to P. And then again, you can write another free body diagram and put your MBA here. Oh my goodness me. MBA and then MAB. And so you can have your shear term. This becomes MAB plus MBA over the length AB, right? Then you just sum them up, okay? And come up with the correct HA and put it in your equilibrium equation. So that these two terms will give you HA, and HD is the same. Okay. And you want me to write HD, maybe, perhaps? And then HD is, this is MCD, this is MDC. So let me say this is HA. And then you can have your HD is equal to MCD plus MDC over the length CD. Okay? And there you have it, your equilibrium equation in the end. HA plus HD, and that should give you P, right? Basic sigma fx equal to 0. Okay? So sigma fx equal to 0, HA plus HD plus P equal to 0. All right? Now let's move on to see something else. Okay. Maybe you can have more than this. This is for the sake of demonstration. I'm not going to kill you by giving you a frame like this, but you should know how things can be handled, okay? Even though I like to say in the class that, hey, this is my exam, when I was a student your age, this is my exam. Okay, so let's say we can have something like this, say P and P. Okay, now if I give this a proper name, A, B, C, D, E, and F, how many unknowns we have?
And I see it before this page again.
Oh, okay, the previous one?
Yeah.
Okay, that is.
Thank you, teacher.
All right, cheers. So let's come back here. So again, the first step would be just to properly identify your unknowns, right? and I feel like dark blue. So let me say this time your unknowns will be theta B. Okay, look like B, theta B, theta C, theta D, theta E, and delta. Now, how many deltas do we have? Actually, one delta per one floor is enough, you know. So this can be your delta 1. And from this floor on, that, you know, the difference, not the total, that can be your delta 2. So 6 unknowns in total, and you can say you are going to need 6 equilibrium equations. And whenever you have the theta, you should have sigma moment, correct? Sigma MB, sigma MC, sigma MD, sigma M equal to 0. They are for your 4 rotations. And when you have this, now because you have 2 floors, so generally you should have like 2 horizontal displacements as unknown, right? But you can only have 1 sigma fx. But you know, in terms of type of equations, it's 1 sigma fx, but we can always have as many sigma fx's as we want. So we're just going to need 2 of them. Okay, so the first one would come from, me try to find different color, this free body diagram. Okay, when you cut that free body diagram, you would have something like this. With the P, all right? And, you know, let's say, you know, the direction is not the stuff the dream is made of, but you need to figure it out, okay? You have HB. I'm writing it in the direction of the moment equation, okay? So it's a bit weird because what you're gonna have next is that you will realize that you have what is this? MCB, MBC, and HB apparently is MBC plus MCB divided by the length BC. Oh, I just got tangled up a little bit. Length BC. Okay, and the next one is, of course, the for another column, MDE, MED. So H, that's C, it should be E. HE is equal to, as usual, MDE plus MED over the length DE. And in the end, just P plus HB plus HE equal to 0. Okay, just be mindful of the direction. And next, That's one more equation. Next is this free body diagram, the entire thing. You can say you cut the free body diagram of the whole, or you don't, okay? So the next is the whole picture. Okay. So you have P, and you have P, and you have this time HA and HF. Okay, and even though, yeah, the base shear of the structure must be equal to the total horizontal load, right? But even though, yeah, we use this free body diagram, your equation will always come from the free body of member AB. And therefore this becomes MBA and MAB. Okay, this will give you the HA, which is equal to MBA plus MAB over the length of member AB. And likewise for member EF, right? So you have MEF, MFE, and then this shear, and you can say HF is equal to MEF plus MFE divided by the length EF. And in the end, your equilibrium equation is 2P plus HA plus HF equal to 0. So of course, you would expect the shear at the base to be greater than the shear on the column on the second floor, and so on and so forth. So that's why, you know, your columns get bigger and bigger and bigger towards the ground. Okay. And you know, I don't do this stuff anymore. I think it's too difficult. So let's skip this and let me find another one for you. Okay. You know, the problem is going to get worse if we have. You want me to stay over this page for a few more seconds, maybe? Are we okay? Well, we are okay then. So let's try something more crazy. Let's say if you have stuff like this. Okay. I have the real problem, but I'm not going to work it out. But maybe I will if we have enough time. But let's say if you have a situation with a frame that looks like this. Okay. Make it shorter so I can draw it more easily. Let's give you the real dimension of the frame, just in case that we may have the opportunity to work on this one. 3 meters. But on this side is 4 meters. This is 1.25 meters. This is 3 meters. And the length in between is 5. So I think I probably could have done a better job on the drawing. Anyway, it has a uniform load. So what do you think? Would this frame sway? What do I expect, right? Total quietness. So it will sway because it's unsymmetric. All right, regardless of whatever you have, but we have the unsymmetric structure, so definitely it would sway. And the sway is crazy. Now, you need to understand that we always need to identify the unknowns correctly first. So let's say if I call this A, B, C, and D, my unknowns would be zeta B, zeta C. And because it's sway, I need the delta, right? How many delta you think I should have? It's one floor, so I should have one delta. But when we have delta this time, just look at this. Okay, let me draw this again. You know, let's say this frame will sway to the left. What will happen is that it will just come to the left a little bit, right? And because of the assumption that, okay, we don't have any axial deformation, so let's say this is delta. So that means this is probably going to have to move delta as well. Not probably, it must move delta as well. But you see, when the right column moves, you see, when this one moves, and you have the rotation of the member, it must maintain its rigidity. So therefore, this has to maintain 90 degrees. So that means joint C will have to move to the left and a little bit downward as well. Right? And likewise, to maintain that, member AB, you know, delta is the same, so it's just gonna have to go up a little bit like that. And to maintain the rigidity, you know, this has to be 90 degrees. So joint B has to move up a little bit as well. And therefore, you know, in the end, this is probably what your frame will look like. Okay, so member AB will rotate to the left, just like member CD. But look at member BC, because of, you know, the inclined column that you have, BC will also rotate. Unlike the straight frame that we have done in the previous example. So BC will rotate as well. So this time, because of, I don't want to say kinky, but it feels that way. Member AB will have the psi. Member CD will have the psi. And member BC will also have this. Again, you see, we identify the unknowns as 3 in total. And because we have one floor, so we should say we have only one delta. So the key to solving a problem like this is to finally turn psi AB, psi BC, and psi CD into the delta term. Okay, so wow, what do you need to do now? we are actually, you know, let's do it for the sake of knowledge. Okay. When you need to calculate the psi term, you need this triangle, right? You need this triangle. But the psi is identified in the horizontal direction. So in order for you to get that, you need to turn this. Let me try again. Let's try to at least draw it with the same slope so that you have a better feeling. Okay. When you want this angle, you want this distance. But because we need to solve this frame as one horizontal unknown, so we identify our unknown in this direction. So you need to turn this delta into the distance in this direction so that you can calculate, you can write psi AB. Okay, so let's say if I call this angle alpha. Okay, this, let's call this one, I don't know, x. Now x is going to be equal to delta over sine alpha, right? Because if that's the angle alpha, that is alpha. Okay? And you can say that sine alpha is equal to delta over x. And therefore you can write like that. Okay? And you are going to need the vertical distance as well. So let's call this one y. And you can say that for y, you need tan theta, tan alpha. And so tan alpha is equal to delta over y. Okay, you can get y from that. And you can do the same with this stuff. So let's call this one beta. Okay. And you are going to need this triangle with that. Okay. So again, if this one is beta, which one's going to be beta? This one, right? That one is beta. And let's say if this is your delta, now you can identify that sine beta is equal to delta over x. Say again that is your x. Okay, this is your x, and your y is this one, tan beta is delta over y. And now that's how we can relate the psi term and write it in terms of delta. So this one is, remember, we assume that it goes in this direction, it's a counterclockwise, so it is minus delta over sine alpha, and then this is the distance, so it has to be divided by the length of member AB, which is 3.25. The length is 3.25. Okay, and the psi CD, that's minus delta over sine beta divided by the length of member CD, that is 5 meters. Okay, and the last one is rather tough. It's a psi BC. That becomes, you know, a y from this term plus the y from that term, because you see from the picture, you know, one side goes up, another side comes down. So it helps increase the angle, right? So that is delta over 10 alpha plus delta over 10 beta, and then divided by the length of member BC, which is 5. Okay, so you probably will not face something like this in real life. In terms of calculation, you may face the frame like this in real life, but I don't think you will have to do the calculation by yourself. I'm just showing you for the sake of demonstration. Okay, so that you know what's going on with this. And when you face the frame with the legs like this, it's when you know you can have the rotation on the horizontal member, such as member BC as well. It's not like you will never ever have the horizontal member rotate. You can when you face a situation like this. Okay, so I don't think anybody would want to ask anything about this frame. Yeah, it's a good knowledge, and yeah, we used to study something like this in the past. So is there any question? Okay, all quiet. So I will stop. It seems like we have a chat. Oh, whoa. What do you mean, whoa? Yeah, it's just like we can have more than whoa, you know. We can have something like this, but I'm not gonna do it because I used to draw this in the class, you know. This, it's gonna be super whoa, you know. Okay, it's very difficult to draw as well. So all right, let's leave it like that. I'm not gonna mess around with this stuff. Okay, that's more than enough. Just this frame to show you that we can have a situation like this, and that would do. Okay. That question about the frame? Perhaps not. So again, let's stop the share. Let's stop the